3,000 wooden ties per mile of railroad track. That's what it takes. Each tie is a hand-cut log, 8 feet long, 8 inches thick, 6 inches wide, cut from a living tree, shaped by hand, transported to the railroad, laid in place. 1 mile equals 3,000 ties. The Transcontinental Railroad was 1,907 miles. That's 5.7 million ties, just for one railroad. By 1916, America had 254,000 miles of railroad track. That's 762 million ties. Every single one cut from a tree, most cut by hand, by men called tie hacks, men who lived in logging camps, men who worked for lumber companies. The railroad industry and the lumber industry weren't separate. They were connected, integrated, dependent. The lumber industry built the railroads, literally. This is how it worked, how logging made railroads possible, how every mile of track required forest to be cut, how the two industries built America together. 1862. President Lincoln signs the Pacific Railway Act, authorizes construction of the Transcontinental Railroad, Union Pacific Building west from Omaha, Central Pacific Building east from Sacramento. They'll meet somewhere in the middle, connect the coasts, unite the nation. But before a single spike gets driven, before a single rail gets laid, someone must cut the ties. Millions of ties. The Transcontinental alone needs 5.7 million. Where do they come from? How do you produce millions of wooden ties? The answer is tie camps, specialized logging camps, focused entirely on cutting railroad ties. Not lumber for buildings, not logs for sawmills, just ties, rectangular timbers, specific dimensions, exact specifications. And railroad companies contract with lumber companies, place massive orders. We need 100,000 ties delivered by spring. We need 500,000 ties for the next 50 miles. We need ties continuously for the next 5 years. The lumber companies respond, establish tie camps, hire tie hacks, begin cutting. The operation is enormous. Industrial-scale logging focused on a single product, railroad ties, the foundation of every railroad in America. The specifications are exact. A standard railroad tie is 8 feet long, 6 inches thick, 8 inches wide at one end, 9 inches wide at the other. Tapers slightly. The taper isn't arbitrary, it's engineered. Ties are laid alternately. Narrow end, wide end, narrow end, wide end. Creates even spacing. Uniform support. If all ties were perfectly rectangular, gaps would vary. Rails would sit unevenly. Trains would bounce, derail. The taper solves this. Simple geometry, practical engineering. The wood species matter. White oak is ideal, dense, strong, rot-resistant, lasts 20 to 30 years in service, but white oak forests are limited. Can't supply hundreds of millions of ties, so other species are used. Red oak, chestnut, cedar, pine, fir, hemlock, each has advantages and disadvantages. Cedar is rot-resistant but soft, wears quickly under heavy loads. Pine is abundant but rots fast, needs chemical treatment. Chestnut is excellent but susceptible to blight. The 1904 chestnut blight eventually kills billions of chestnut trees, eliminates a major tie source, forces railroads to adapt, use different species, develop preservative treatments. But in the 1860s through 1880s, cutting natural ties from durable species is standard. Find a white oak forest, cut ties, ship them, install them. Tie hacks are specialized workers, not regular loggers, not sawmill workers, dedicated tie cutters. The name hack comes from the tool, the broadaxe, sometimes called a hacking axe, a massive tool. Blade may be 12 inches wide, weighing 5 to 8 pounds, sharpened to razor edge, used for hewing logs into rectangular timbers, shaping round logs into square ties. The tie hack's job is simple in concept, brutal in execution. Find a suitable tree, usually 8 to 12 inches in diameter, minimum. Bigger if available, cut it down, buck it into 8-foot sections. Each section becomes one tie. Then hew each section. Use the broadaxe, remove bark, Flatten sides, create rectangular shape, exact dimensions, the work is backbreaking. A skilled tie hack can produce 6 to 10 ties per day, working alone. 12 hours of hard labor, swinging the broad axe, shaping wood, repeating endlessly. The daily output seems low, but multiply by hundreds of men, working daily for months. The volume accumulates. 100 tie hacks producing 8 ties per day equals 800 ties daily. Over a 6-month season, that's 144,000 ties from a single camp, multiple camps operating simultaneously. The numbers work, the ties get cut. If you're the kind of person who believes these stories deserve to be remembered, hit subscribe. The tie hacks who cut millions of railroad ties are almost completely forgotten. No photographs, barely any records, just vague mentions in lumber company archives. But they made railroads possible. Subscribe if you think they deserve recognition. The process starts with selecting trees. The tie hack walks through the forest, examines trees, looks for straight trunks, minimal taper, no major branches below 8 feet, no obvious defects, rot, hollow sections, split wood. A perfect tie tree grows straight, minimum 8 inches diameter at 8 feet height, ideally 10 to 12 inches. Provides enough wood after hewing. The tie hack marks suitable trees, uses a marking axe, chips a small blaze, or paints a spot, marks dozens of trees, maybe 100, then returns with his felling axe, begins cutting. The felling axe is different from the broad axe, lighter, 3 to 4 pounds, designed for chopping, cutting across grain. The tie hack cuts a notch on one side. The undercut determines falling direction, then cuts from the opposite side, the back cut, slightly higher than the undercut, and creates a hinge. The tree falls, crashes down. The tie hack moves to the next tree, repeats, falls 10 to 20 trees before stopping, then switches to bucking, cutting the felled trees into sections. Bucking is done with a crosscut saw, 1-man or 2-man depending on diameter. For 8 to 12-inch trees, a 1-man saw works. 4 to 5 feet long, handles on both ends. The tie hack measures 8 feet from the butt, marks it, positions the saw, begins cutting, pulls, pushes. The saw teeth bite, remove wood, create sawdust. The cut takes maybe 5 to 10 minutes, depends on wood hardness, diameter, saw sharpness. When the section is nearly through, it drops, falls free. The tie hack measures another 8 feet, cuts again, repeats until the trunk is completely bucked. A 40-foot tree yields 5 ties. A 60-foot tree yields 7 or 8. The top sections, too small diameter, get left, wasted. Only sections with sufficient diameter become ties. This means significant waste, maybe 30 to 40% of each tree. But tie specifications are exact, can't compromise. Undersized ties fail, rails spread, trains derail. Better to waste wood than risk failures. Now comes the hewing, the hardest work, the most skilled work, the defining work of a tie hack. Each 8-foot log section lies on the ground, round, bark-covered, irregular, must become rectangular, smooth, exact dimensions. The tie hack uses a broad axe. The tool is specialized. The head is asymmetric, one side flat, one side beveled. The flat side faces the wood, the bevel faces away. This creates a cutting action that produces flat surfaces. The tie hack stands on top of the log, positions it, sometimes uses log dogs, metal spikes to hold it steady. Begins swinging. The broad axe is heavy, 5 to 8 pounds, on a handle maybe 2 to 3 feet long. The tie hack lifts it, swings down, strikes the log, removes a chip, lifts, swings, strikes, removes another chip. The motion repeats hundreds of times per tie. The blade must stay sharp. Dull blades bounce, don't cut cleanly. Require more swings, more effort. Tie hacks sharpen constantly. Carry whetstones, files. Stop every hour or two. Sharpen the blade, return to work. The hewing pattern is methodical. Start with one side, remove bark, begin flattening, work from one end to the other. The goal is a flat surface, not perfect, not plain smooth, just flat enough. The railroad doesn't need furniture quality finishes. Needs functional supports. Once one side is done, roll the log. Do another side, then another, then the fourth. Each log section gets 4 sides hewn, 8 inches by 6 inches, from a log that was maybe 11 or 12 inches diameter. Substantial wood removed, lost, becomes chips. Scattered on the ground, left to rot. The waste is enormous but necessary. After all 4 sides are hewn, the tie is complete. Rough, splintery, but correct dimensions. Functional. The tie hack drags it aside. Starts the next one, 6 to 10 ties per day. Day after day. Week after week. Month after month. The work is monotonous, exhausting, dangerous. Let's examine the technique in detail. The tie hack positions the log, usually on smaller logs used as supports, elevates it off the ground, maybe 12 to 18 inches high. This height prevents the broadaxe from hitting dirt, rocks, damaging the blade. The log is secured, sometimes with log dogs, large metal staples driven into the wood, hammered in. Hold the log steady, prevent rolling. The tie hack stands on the log, straddles it, feet shoulder-width apart, knees bent, weight balanced. The broadaxe rests beside him. He picks it up, grips the handle, tests the balance. The handle is maybe 30 to 36 inches long, shorter than a felling axe. Allows more control, more precision. The head weighs 5 to 8 pounds. The blade is 12 inches wide, maybe more. Ground to a fine edge, sharp enough to shave hair. The cutting edge must be perfect. Any nicks, any dull spots, the blade bounces, doesn't bite, wastes energy. The tie hack lifts the axe, raises it overhead. Not a full overhead swing like felling. More controlled, shorter arc, brings it down, strikes the log, the blade bites, removes a chip, maybe 1 to 2 inches wide, 1/4 inch deep. The chip flies off. The tie hack lifts again, strikes adjacent to the first cut, removes another chip, repeats, moving along the log's length. Each strike removes a small section, gradually flattening the surface. The rhythm is constant. Lift, swing, strike, lift, swing, strike. Maybe 20 to 30 strikes per minute, for hours. The physical toll accumulates rapidly. The broadaxe weighs 5 to 8 pounds. Doesn't sound heavy, but lifted overhead 30 times per minute, for 60 minutes. That's 1,800 lifts, times 5 pounds minimum. That's 9,000 pounds lifted per hour, 4.5 tons. Over a 10-hour day, that's 45 tons, lifted and swung, repeatedly. Your shoulders burn, the deltoid muscles. The trapezius, the rotator cuff, microscopic tears form, inflammation, pain. But you continue, no breaks, no rest. The pain becomes constant, permanent. Old tie hacks have destroyed shoulders, can barely lift their arms, arthritis, bone spurs, torn tendons. The damage is cumulative, irreversible. Your back suffers similarly. Standing on an unstable log, bending, straightening, twisting, swinging. The lumbar spine compresses. The vertebrae grind. Discs bulge. Nerves pinch. Lower back pain becomes chronic, debilitating. Every movement hurts, but the work continues, must continue. Income depends on production. No work, no pay. Injury means poverty. So you work through pain. Ignore signals your body sends. Push until something breaks. Then you're done, crippled, unable to work, discarded. The hands take particular abuse. Gripping the axe handle, 10 hours daily. The pressure creates calluses, thick layers of dead skin, protective but painful while forming. Blisters form first, fill with fluid, pop, bleed, reform as calluses. The skin hardens, becomes leather-like. But before that transition, every swing hurts. Blood makes the handle slippery, grip weakens, accidents become more likely. The constant vibration from impacts damages nerves, causes numbness, tingling, loss of dexterity. Old tie hacks can't feel their fingers properly, can't perform fine motor tasks, can't write, can't button shirts. The nerve damage is permanent. No treatment exists. Just live with it. Accept it. The alternative is starve. So men work until their bodies fail, then die young. Broken, forgotten. The danger of the broadaxe cannot be overstated. The blade is massive. 12 inches wide, razor sharp, swung with full force, aimed at wood, but sometimes it misses, hits flesh instead. The most common injury is to the leg. The tie hack stands on the log, swings down, the axe glances off, continues downward, strikes his shin, cuts through pants, through skin, through muscle, sometimes hits bone, splits the tibia. The pain is instant, overwhelming. Bleeding is profuse. The wound gapes. Bone might be visible. White splinters. The tie hack is alone. Miles from camp, miles from help. No first aid, no medical kit, just his shirt. He tears it, wraps the wound, applies pressure, tries to stop bleeding. If successful, he limps back to camp. Takes hours, days if the injury is severe. At camp, there might be basic medical supplies. Bandages, whiskey to sterilize. That's it. No doctor, no surgeon, no antibiotics. The wound gets cleaned, wrapped, left to heal. Or not. Infection is common, nearly guaranteed. The wound turns red, swells, oozes pus. The infection spreads up the leg into the bloodstream. Sepsis develops, fever, chills, delirium. Without antibiotics, survival is chance. Luck, constitution, many die. Their bodies are buried near the camp. Unmarked graves, no records, just gone. Replaced by new workers who arrive knowing the risks, accepting them, because they need money, need work, need to survive. Head injuries from falling branches are another constant danger. The tie hack works beneath standing timber. Living trees, dead trees, dying trees, wind blows, branches fall, dead limbs, called widowmakers, break loose without warning. Drop silently, strike the worker below. A 4-inch diameter branch falling 40 feet hits with enormous force, enough to fracture skulls, cause concussions, kill instantly. The tie hack has no warning, no time to react. One moment he's working, the next he's unconscious or dead. Co-workers might find him, might not. Working alone means death often goes undiscovered for days, until someone investigates, finds the body, cold, decomposing. The cause is obvious, branch lying beside him, no mystery, just bad luck. The body gets buried. Operations continue, no investigation, no safety review, just another death. Accepted, expected, part of the job. Extreme weather creates additional hazards. Summer work means heat. Temperatures exceed 90 or 100 degrees Fahrenheit. Direct sun, no shade. The tie hack swings the heavy axe, generates enormous body heat, sweats profusely, loses water. Salt, electrolytes. Dehydration is rapid, heat exhaustion is common, heat stroke is deadly. The symptoms progress, weakness, dizziness, confusion, collapse. Without intervention, death follows quickly, but intervention requires someone nearby. Seeing the symptoms, responding. Tie hacks work alone. When heat stroke hits, they collapse, alone, no help, no water, no cooling. They die where they fall. Their bodies get discovered days later, bloated, decomposed, unrecognizable sometimes. Winter work is equally dangerous. Different hazards, same mortality. Temperatures drop below freezing, far below, 0, 10 below, 20 below. The tie hack must keep working, generate body heat, maintain circulation, but extremities suffer, fingers, toes, nose, ears, frostbite develops, the tissue freezes, blood stops flowing, cells die. Initially, unfrostbitten areas hurt, burn, sting, then numbness, complete loss of sensation. This is dangerous. The tie hack doesn't feel injuries, doesn't realize the damage, keeps working. By the time he returns to camp, fingers are frozen solid, black, dead. They must be amputated, sometimes at the first knuckle, sometimes the entire finger, sometimes multiple fingers. The amputation is crude. A knife heated in fire cuts through frozen tissue, cauterizes. The pain is indescribable. Many men lose fingers, toes, noses, ears, carry the scars permanently, visual reminders of winters in tie camps. The dangers are constant. The broad axe is razor sharp, weighs 5 to 8 pounds, swung with full force, hundreds of times per day. Miss the wood, hit your leg, slice through pants, cut deep into flesh, sever tendons, break bones, arteries. Bleed out in minutes in a remote forest, miles from help. Tie hacks work alone usually, no partners, no help nearby. An accident means death. How many died? Unknown. Tie camps didn't keep detailed records, especially early camps. 1860s, 1870s. Men disappeared, died, got buried in unmarked graves, new workers hired, operations continued. The death toll across all tie camps over 50 years probably numbers in the thousands, maybe tens of thousands. No one counted, no one cared. The work was dangerous. Everyone knew. Workers accepted the risk because the pay was slightly better than regular logging. Maybe $2.50 to $3.50 per day. That's $80 to $112 modern. For piecework, payment per tie produced, not hourly. Produce more ties, earn more money, work faster, risk more. The incentive structure encouraged speed. Speed meant accidents. Accidents meant deaths. But the ties got cut. That's what mattered to the companies. These men didn't have YouTube channels. They didn't have anyone telling their story. We're changing that. The tie hacks cut hundreds of millions of ties, made transcontinental railroads possible, made industrial America possible. Subscribe if you think their work matters. If you think we should remember who actually built this country. The camp life is brutal. Tie camps are temporary, located near suitable timber, not near towns, not near civilization, just forests. The workers live in rough bunkhouses, log cabins, tents sometimes, maybe 20 to 50 men per camp, bunks stacked 2 or 3 high, 18 inches between levels. No privacy, no personal space, just sleep, eat, work. The food is basic, high calorie, fills you up, beans, bread, salt pork, coffee, potatoes, maybe fresh meat when hunters succeed. No vegetables most of the year, no fruit. Scurvy is common. Vitamin deficiencies, health deteriorates. The work is so physically demanding that men burn enormous calories, eat massive portions, still lose weight, muscle breaks down, bodies consume themselves. A season in a tie camp ages a man. Permanently. The camps are all male. No families, no women, no children, just workers. The social isolation is crushing. Months without seeing anyone except the same 40 men. No entertainment, no distractions. Some camps allow gambling, card games, dice, others forbid it. Too many fights, too many deaths over debts. Some camps provide alcohol, others are dry, company policy varies. Either way, conditions are miserable. Men endure them because they need money. Need to eat. Need to survive. The alternatives are worse or non-existent. Transportation is the next challenge. The ties are cut, stacked in the forest, miles from the railroad. How do they get delivered? Multiple methods depending on terrain and season. In winter, sleds. Large wooden sleds pulled by teams of oxen or horses. Each sled carries maybe 20 to 50 ties, weighing several tons. The teams haul them over snow and ice to a river landing, or directly to the railroad if close enough. The winter months are ideal for moving heavy loads. Snow and ice reduce friction, make pulling easier. In spring and summer, the ties float, get rolled into rivers, creeks, streams, float downstream, collected at booms, sorted, rafted together, towed to mills or to railroad sidings. Water transport works well for ties. Unlike boards, ties don't need to stay dry, don't need protection from weather. They're going into the ground anyway. Getting wet doesn't damage them, may even help. Waterlogged ties are heavier, settle better. Some railroads specify season ties. Cut 1 year, installed the next. Gives wood time to dry, stabilize, reduces warping. Others install green ties, freshly cut, still full of moisture. These settle and compress more. Railroad companies have different standards, different specifications. The tie camps adapt, produce whatever the customer wants. The numbers are staggering. Let's calculate precisely. The Transcontinental Railroad, 1,907 miles, times 3,000 ties per mile, equals 5,721,000 ties. Each tie is approximately 0.2 cubic feet of wood. That's 1,144,200 cubic feet of timber. In board feet, the standard lumber measurement, each tie is about 24 board feet. That's 137.3 million board feet for the Transcontinental. Now expand nationally. By 1916, America has 254,000 miles of railroad track. That's 762 million ties, times 24 board feet per tie, equals 18.3 billion board feet of lumber, just in ties, just in active use. This doesn't count the ties replaced over the decades. Rotted ties, damaged ties, worn ties. Every tie lasts maybe 20 to 30 years on average, then must be replaced. Over 50 years of railroad operation, 1865 to 1915, the replacement rate is enormous. Probably 2 to 3 complete replacements. That's 40 to 55 billion board feet of timber consumed just for railroad ties. Then add bridges, trestles, station buildings, freight platforms, rail cars, cabooses, all wood in early years. The total lumber consumption for railroads probably exceeds 100 billion board feet over that 50-year period. That's approximately 1 trillion board feet if you include the broader infrastructure. To put that in perspective, 1 billion board feet is enough lumber to build 100,000 typical houses. 1 trillion board feet could build 100 million houses. The railroad industry consumed enough wood to house the entire American population several times over. This lumber came from forests. Specific forests, targeted forests. Railroad companies didn't own most of this land. They contracted with lumber companies, with independent loggers, with timber speculators. They created massive demand, drove logging into new regions, opened forests that weren't economically viable before. If a railroad wants to expand through Montana, they need ties. Millions of ties. They contract with lumber companies in Montana. Those companies establish camps, hire tie hacks, start cutting. Within a year or two, entire forests are cleared. The ties shipped to the railroad, get installed. The railroad reaches new territory, needs more ties. The cycle repeats. The railroads drove logging expansion across America, provided the economic incentive, the guaranteed market, the steady demand. Without railroads, much of American logging wouldn't have been economical. The market wouldn't have existed. The scale wouldn't have justified the investment. If you want to go deeper into these stories, if you want early access to videos before anyone else sees them, join the membership. It's for people who don't just watch history, they carry it forward. The connection between logging and railroads shaped America. Understanding one industry requires understanding the other. Join the membership if you want complete stories, not just fragments. The railroad tie market was massive and lucrative. A tie in 1870 cost the railroad about 50 cents delivered. That's $16 modern. For 3,000 ties per mile, that's $1,500 per mile. That's $48,000 modern, just for ties. Not rails, not labor, not grading, just the wooden foundation. Multiply by 254,000 miles. That's $381 million in 1870 dollars. That's $12.2 billion modern, just for ties. The lumber companies supplying these ties made fortunes. Not individuals necessarily, but companies. The large operations, those with capital, equipment, expertise. Small operators couldn't compete, couldn't meet the demand, couldn't deliver the volume, didn't have the infrastructure, and the railroad tie market consolidated the lumber industry, favored large operations, drove industrialization, changed logging from a local small-scale activity to a national industrial enterprise. The railroads created the modern lumber industry by creating massive sustained demand, by requiring industrial-scale production, by making large operations profitable and small operations obsolete. Quality control became critical as the market grew. Early railroads accepted almost any tie, rough dimensions, variable quality, inconsistent species. But problems emerged quickly. Poor quality ties failed prematurely. Rails spread. Trains derailed. People died. Lawsuits followed. Railroad companies realized quality mattered, began specifying standards, detailed specifications. The ties must be straight. Maximum deviation, 1 inch over 8 feet. Any more and the tie is rejected. No large knots. Knots weaken the wood, create failure points. Knots larger than 2 inches diameter mean rejection. No splits, cracks, checks. These allow water penetration, accelerate rot, compromise strength, no heart rot, interior decay, common in older trees. The inspector probes with a metal rod, pushes into the wood, feels for soft spots, voids. Any rot means rejection. No sapwood on edges. The outer layer of the tree, less durable than heartwood. Rots faster, wears quicker. The tie must be predominantly heartwood, dense, strong, durable. These standards eliminate maybe 20 to 30% of production. 1 in 4 or 5 ties gets rejected. This waste is built into pricing. Expected? The railroad pays for quality, gets it, or rejects the entire shipment. Inspection happens at multiple points. First, at the tie camp. Company inspectors examine finished ties, measure dimensions, check straightness, look for defects. Rejected ties get thrown aside, not paid for, represent pure loss to the tie hack. This creates tension, incentive to hide defects, turn bad ties upside down, conceal rot, disguise problems. The inspectors learn, develop techniques, check both ends, all 4 sides, random deep probes, catch hidden defects, reject questionable ties. Better to reject marginal ties than accept failures. The second inspection happens at delivery, rail yards, distribution points, different inspectors, fresh eyes, independent assessment. They re-examine everything, measure again, probe again, reject ties that passed camp inspection. Maybe 5 to 10% more rejections. The cumulative rejection rate can reach 35%. 1 in 3 ties cut doesn't meet standards, never gets installed, becomes waste, firewood, scrap. The economics still work. The demand is enormous. The price is adequate. Even with 35% rejection, profit remains. The species hierarchy becomes standardized through experience. White oak is universally recognized as superior. Durability, strength, longevity, commands premium prices, maybe 75 cents per tie delivered. That's $24 modern. Next is chestnut, before the blight. Nearly as durable as white oak. Slightly lighter, easier to work. Sells for 60 cents to 70 cents per tie. Then red oak, harder than white oak, more brittle. Splits more easily, but available, acceptable. Sells for 50 cents to 60 cents. Cedar follows. Excellent rot resistance, but soft. Wears quickly under heavy traffic. Suitable for light use branch lines, not main lines. Sells for 40 cents to 50 cents. Then pine and fir, abundant, cheap. Rot quickly without treatment. Lasts maybe 10 years untreated, but plentiful, easily sourced. Sell for 30 cents to 40 cents. Hemlock is bottom tier, weak, rots fast, splits badly. Used only when nothing else is available. Sells for 25 cents to 30 cents. The market stratifies by species. Quality, durability, price. Railroads specify preferred species. Accept substitutes when necessary, pay accordingly. The piecework payment system drives productivity and accidents simultaneously. Tie hacks aren't paid hourly. They're paid per tie. Maybe $0.08 to $0.12 per acceptable tie in the 1880s. That's $2.56 to $3.84 modern. Produce 10 ties per day. Earn 80 cents to $1.20. That's $25.60 to $38.40 modern for 10 to 12 hours of brutal labor. The math encourages speed. Work faster, produce more, earn more, but speed increases accidents, increases rejection rates. A tie hack rushing makes mistakes, cuts himself, cuts ties too rough, gets rejections, loses income. The balance is delicate. Work fast enough to earn decent money. Not so fast you get injured or rejected. Experienced tie hacks find the sweet spot, maintain steady pace, consistent quality, reasonable safety. Novices struggle, rush too much, get hurt, or go too slow. Don't earn enough, quit or starve. The system is brutal, unforgiving, efficient, maximizes production while minimizing labor costs. The companies profit enormously, the workers barely survive. This is the industrial reality of tie production. Exploitation clothed in piecework. Justified by market rates, accepted because alternatives don't exist. Camp bosses monitor production closely, track each worker's output, daily counts, weekly totals, seasonal summaries. The numbers are recorded, workers ranked, the top producers get better treatment, respect, sometimes bonuses. The poor producers get harassed, threatened, eventually fired, replaced. The camp boss's job is maximizing production, delivering contracted quantities, meeting deadlines. He doesn't care about worker welfare, about safety, about fairness. Just numbers, ties produced, ties accepted, ties delivered. His bonus depends on meeting quotas, exceeding them. So he pushes workers, demands more, always more. The pressure is constant, relentless. Workers internalize it, push themselves, compete with each other, try to be top producer, earn recognition, job security. The system pits workers against each other, prevents solidarity, prevents organizing, prevents demands for better conditions. This is intentional. Company policy. Keep workers divided. Keep them competing. Keep them desperate. Control is maintained through economic pressure, through fear, through replacement threats. The workers understand, comply, have no choice. This is how the system functions, how millions of ties get produced, how railroads get built, on the broken bodies of tie hacks, forgotten, unremembered, uncompensated. The transition to mechanical production is gradual but inevitable. In the 1880s, portable sawmills appear in forests, steam-powered, mounted on wheeled frames, can be moved, set up near timber stands. These mills cut ties more efficiently than hand hewing. A circular saw cuts through a log in minutes. What takes a tie hack hours? The mill can process dozens of logs per day, hundreds of ties. The cost per tie drops, quality improves, dimensions are exact, consistent. The hand-hewn ties can't compete. Vary too much, take too long. Cost too much when labor is factored accurately. The sawmills proliferate. By 1890, probably half of all ties are sawn. By 1900, maybe 80%. By 1910, hand-hewn ties are rare, anachronisms, produced only in the most remote locations, where mills can't reach, can't operate profitably. The last tie hacks work in these marginal areas: Appalachian hollows, Rocky Mountain canyons, Pacific Northwest islands, places where terrain prevents mill installation. But even these areas eventually get reached. Mills become more portable, more efficient, more economical. By 1920, hand-hewn ties are essentially extinct. The occupation disappears, the skills vanish, the knowledge dies with the practitioners. A few old-timers remember, tell stories, but the details fade, the techniques are lost. Nobody teaches broad-axe hewing anymore. Nobody needs to. The industrial age has arrived. Mechanization is won. Human labor, at least this kind of human labor, is obsolete. The tie hacks are forgotten. Their contribution erased. Their suffering unremembered. This is progress, efficiency, advancement, but something human is lost. Some connection to material, to craft, to the direct transformation of tree into railroad tie. That connection mattered, still matters, deserves remembrance. The chemical treatment industry emerged from this. Early ties were untreated. Natural wood. They rotted, especially in humid climates. The southern states, Pacific Northwest. Even white oak, the most durable species, lasted maybe 20 years. Other species lasted 10 years or less. Railroads faced enormous replacement costs, constant maintenance, disrupted operations. The solution was chemical treatment. Preservatives, creosote primarily, coal tar creosote, a thick, oily liquid, distilled from coal tar, contains hundreds of chemical compounds, toxic to fungi, insects, bacteria, everything that causes wood rot. Tie treating plants emerged in the 1870s, large industrial facilities. The process is sophisticated. Ties are loaded into huge pressure vessels. Cylinders may be 100 feet long, 6 feet in diameter, hold hundreds of ties. The cylinder is sealed, air is evacuated, creates vacuum, opens the wood's pores, then hot creosote is pumped in under pressure. It forces the chemical deep into the wood, penetrates inches, sometimes clear through on thinner sections. The treatment takes hours. When complete, the ties are removed, allowed to cool. The creosote solidifies, creates a protective layer. Treated ties last 50 to 60 years. Triple or quadruple the lifespan of untreated ties. The economics are obvious: pay more upfront, save enormously over time. By 1900, most major railroads required treated ties, created another industry, another market, another connection between railroads and lumber. The labor force overlapped. Men worked as tie hacks in winter, worked laying track in summer. The seasonal nature of both industries aligned perfectly. Tie cutting happened in fall and winter. When sap is down, wood is drier, easier to work, easier to transport on snow. Track laying happened in spring and summer, when weather permitted, when ground wasn't frozen. The same men transitioned, worked both jobs. Same companies often employed them. Lumber companies contracted to supply ties and lay track. Vertical integration, control the supply chain, maximize profits. A company with tie camps and track laying crews could bid lower, complete projects faster, deliver better value. This is how the industrial lumber companies grew. Started with logging, expanded to tie production, then to track laying, then to rail car manufacturing, then to locomotive repair. Vertical integration across the entire railroad supply chain. Companies like Weyerhaeuser, Simpson, Boise Cascade started in logging, grew into industrial conglomerates. Railroad demand enabled this growth, provided the capital, the market, the opportunity. The environmental impact was catastrophic. Every mile of railroad required cutting roughly 3,000 trees. Minimum, often more, accounting for waste and defects. 254,000 miles means roughly 760 million trees, just for the ties, just for the initial installation. Add replacements over 50 years. Triple that number, 2.3 billion trees, just for railroad ties. Then add all the other railroad lumber needs, bridges, buildings, equipment. The number probably exceeds 5 billion trees. 5 billion trees cut primarily for railroads, over 50 years. That's 100 million trees per year, every year, for half a century. Forests don't regenerate that fast, especially old-growth forests. The trees cut for ties were typically 50 to 100 years old, sometimes older. Cutting them meant permanent loss, no replacement, no regeneration within human timescales. The eastern forests were devastated. Pennsylvania, New York, West Virginia, Virginia. By 1900, old growth was essentially gone, replaced by second growth, younger forests, smaller trees, lower quality timber. The logging moved west, to the Great Lakes region, Michigan, Wisconsin, Minnesota. Those forests were depleted by 1920. The logging moved further west, to the Pacific Northwest, Washington, Oregon, Northern California. By 1950, even those forests were heavily cut. The railroad industry's demand drove this progression, this depletion, this destruction. The environmental cost was never calculated, never compensated, never acknowledged, but it was real, permanent, irreversible. The technology evolved. Early ties were hand-hewn. By the 1880s, sawmills entered the business. Could cut ties more efficiently, power saws, steam-powered mills, cut logs into precise dimensions, faster than hand hewing, more consistent, less waste. A sawmill could produce hundreds of ties per day, thousands per week, far exceeding hand production. The tie hacks couldn't compete, gradually became obsolete. By 1900, most ties were sawn, not hewn. The tie hack profession declined, disappeared. The last tie hacks probably worked into the 1920s or 1930s in remote areas where sawmills hadn't penetrated, but eventually they're all gone, replaced by industrial production, mechanization, efficiency. The hand skills were lost. Nobody teaches broadaxe technique anymore. Nobody needs it. The knowledge died with the last practitioners. What remains are a few tools in museums, a few photographs, vague descriptions in old documents. The details are gone, lost, forgotten. The connection between logging and railroads is fundamental. Understanding one requires understanding the other. The railroad industry created massive lumber demand, drove logging expansion, funded industrial-scale operations, enabled lumber companies to grow, consolidate, dominate. Without railroads, the lumber industry would have been smaller, localized, limited. With railroads, it became national, industrial, essential. The railroads needed lumber. The lumber industry needed railroads for transportation, for markets, for access to timber. The relationship was symbiotic, mutually beneficial, mutually dependent. You couldn't build railroads without lumber. You couldn't transport lumber efficiently without railroads. The two industries built each other, built America together. This is why railroad content matters to logging audiences, why it's relevant, why it's connected. Every railroad video is also a logging video. Every discussion of track is also a discussion of lumber. Every mile of rail represents 3,000 trees, 72,000 board feet. Forests converted to infrastructure, timber made into transportation. The connection is literal, physical, undeniable. Modern railroads still use wooden ties. About 90% of ties in America are still wood. The rest are concrete or composite materials. Wood remains preferred. It's flexible, absorbs vibration, insulates electrically, can be easily worked, drilled, spiked, replaced. Concrete ties are rigid, crack, break, difficult to install, expensive. Composite ties are experimental, unproven, may not last. Wood works, has worked for 150 years, will probably work for another 150. But modern ties are different. They're industrial products, cut by machines, treated in factories, transported by trucks, installed by machines. Humans are largely removed. The process is mechanized, efficient, faster, cheaper, but something is lost: the connection to the forest, the understanding that these ties were once living trees, cut by hand, shaped by hand, placed by hand. That knowledge is important. That context matters. When you see railroad tracks, you're seeing logging history. You're seeing forests converted to infrastructure. You're seeing the labor of men who worked in dangerous conditions for low wages, who cut millions of trees, who built the foundation of modern America. They deserve remembrance, recognition, understanding. This is their story, not complete. Too much is lost, but enough. Enough to know they existed, enough to know what they did, enough to honor their contribution. The tie hacks, the lumber camps, the forests that became railroads. This is the connection. This is why it matters. This is what we remember.